Hello, everyone. Let me introduce myself. I'm Gabriel Kleinlunz. I'm a master's student at Federal University of Santa Catarina. And today's presentation is a part of the research for my dissertation, supervised by Professor Henrique Simas, also from the same university. As you can see in the screen, our topic today is about challenges and opportunities for pseudo-continuum robots in single port access, transluminal, and interluminal surgeries. I've divided my presentation into 5 main parts. I'll start with a motivation, then I will look at the common medical classification and challenges for minimally invasive surgery, MIS for short. The third and fourth part is about classifications from an engineering point of view. And finally, I will summarize the open problems and research opportunities. So let me start by giving you some background information. In 1806, Filippo Zini produced the first endoscope with a light source. His revolutionary development involved a series of mirrors to reflect the light from a burning wax candle inside an aluminum device, and this device is considered the first true endoscope. Advances continued into 19th century with devices of Desormeaux and Kelling. Well, during the beginning of the 20th century, we had other advances, mainly with regard to visualization, such as the development of optical fiber technology in 1954. So there was enough technology to have a clear vision of internal cavities, and understanding the great potential of laparoscopy, the surgeon Kurt Sam performed the first laparoscopic appendectomy in 1981. And since then, he has been called the father of modern laparoscopy. So let's move to the 90s, when minimally invasive surgery went through another major evolution. The challenges such as the need to manipulate multiple tools through multiple access routes led to the beginning of robot-assisted surgery. This breakthrough culminated in the first release of the Da Vinci system by Intuitive Surgical in early 2000s. In the nutshell, the Da Vinci teleoperated robot is a system where the surgeon manipulates the master input device in an immersive viewing console. Even with these advances, there are still procedures that require more invasive techniques, capable of reaching difficult to access locations by nonlinear paths. Some authors identified in this article describe the first approach to the continuous robot concept and hyper-redundant robot prototypes dating from the late 1960s. Several articles have since been published talking about hyper-redundant, snake-like robots, soft robots, and so on. Thus, it's important to find ways to classify and organize these new technologies. The classification presented in this slide is based on the nature of the access routes to the surgical site. That said, we can see that there are 2 main approaches to minimally invasive surgery. The extraluminal surgery involves making incisions in the skin to access the internal anatomy. These procedures are classified into multi-port and single-port access, or SPA procedures. The second approach is the interluminal surgery, which includes endoluminal and transluminal procedures. The endoluminal procedures involve operating within a body lumen that can be accessed through a natural orifice, and transluminal procedures also use access along body lumens, but require an incision in the lumen walls to access the surgical site. By definition, these surgeries are called natural orifice transluminal endoscope surgery, or NOTES for short. So you can imagine that this new surgical paradigm brings with it some difficulties for surgeons, which are great opportunities to be investigated by researchers in the field of robotics. In addition to the lack of sensory feedback, the unique architecture of interluminal and SPA robots needs to be able to traverse access routes along turtles' anatomical passages. So at this point, we know how we can classify procedures, but how can we classify these snake-like robots? When a robot has more degrees of freedom than necessary to perform a task, it can be considered redundant, or in extreme cases, hyper-redundant. So as the number of joint approaches infinity, the length of the links approaches 0. In this case, the robot approaches what is known as the continuous robot definition. However, the boundary separating continuous robots from other hyper-redundant manipulators is sometimes difficult to verify. For this reason, the terms pseudo-continuous or serial-continuous have emerged, but it is still possible to notice a lack of consensus regarding the classification of robotic devices. It was observed that a scenario is being built where the classification takes place not only concerning its structural design, but also in terms of its actuation strategy. For this reason, this work contributes with some classification suggestions regarding the structural design, the operating strategy, and the surgical purpose. This suggested classification covers three typical classifications for a continuous robot, taking into account the actuation principle, intrinsic or extrinsic, or hybrid actuation, or even with the structural characteristics mentioned in previous slide. In this way, it's possible to verify if the robot has a discrete and serial structure using cable, tendons, or micromotors. And we can also verify if we are dealing with a robot with an elastic and continuous structure, also using cables, tendons, shape memory, smart materials, or pneumatic and multi-backbone, or even concentric tube, organ-based, or magnetic actuated. So let's move on to how all these classifications are summarized through the most common surgical applications. First, we have the neurosurgery, where the thin concentric tubes enable a new range of procedures for surgery, where regions within the brain can be reached through curvilinear or nonlinear paths. And then in otolaryngology, mouth and nose are used as access to various regions of human body for a variety of surgeries and treatments. In cardiac surgery, robots can be used to valve replacements, repairs or closure of septal defects procedures, and continuous robots can be miniaturized to the scale needed to provide flexible site access and dexterity in procedures in neurology, such as transurethral surgery with multi-backbone robots. And then for vascular surgery, the major problem for surgeons is to control steering as delivering the right amount of force and torque. So far, we can see that in the challenges and opportunities in designing of pseudo-continuous robots, the basic component is the kinematic structure used to represent the geometry, which can be represented from a discrete hyper-redundant structure to a flexible element with constant curvature. Thus, the most widespread kinematic structure was the discrete approach, where a series of rigid links connected by a conventional joint is described using a series of homogeneous transformations generated from Denavi-Rattenberg parameters. The elastic and continuous structures can also have a good representations approximated by hyper-redundant discrete models. In medical application, efforts in the cited works have been concentrated on modeling direct kinematics and static deflection problems. It was also noted that control has usually been approached from a quasi-static inverse kinematic perspective. Even though great progress has been made in designing, modeling, control, sensing, and application to specific medical problems, we are still in transition. Among the challenges and open questions presented on this slide, I would like to highlight the opportunities in develop shape sensing methodology, having an adaptive stiffness characteristic, and operate in the way called follow the leader, where the device body conforms to follow the same path taken by its final effector. This type of movement comprises both a design problem and a control problem, as we can see here in med robotics device. So thank you all for your attention. I hope you found this presentation useful, and now I will be glad to receive any questions and or comments you may have, even by the email indicated in this slide.